And we're now recording. All right, so this is the last lecture on material in astronomy that I have for Astro 25 for our spring class in 2020. It is material that I put together mainly for my Astro 3 class, and there's also material in here that is relevant for Astro 4, which is on cosmology, because it has to do with the nature of the universe itself and how that can be agreeable for life, because there are some arguments that can and have been made, which we now realize we can get around those arguments. We can answer those arguments with new understandings about cosmology itself. So actually stuff very different than biology. All right, so these are the things we're going to talk about. Onward. So what criteria must something have before you call it alive? I mean, we can't talk about life in the universe without knowing what the heck we're talking about. So here's some that most people agree on. There are sort of wider and narrower versions of what some people would want to call life out there. I guess I could say there's no completely agreed upon definition of life, but I think these are at least bare minimums. So it must be able to reproduce itself. If it can't reproduce, then, geez, what is it? A machine? Of course, even a machine's going to reproduce. So it must take in nutrients and energy from the environment to accomplish its goals. It must be able to fight for some kind of a niche in the other life forms that it competes with on its planet or wherever it is. So that puts some pretty strong constraints on what kind of complexity must be involved. And it must be capable of evolving to keep its competitive edge. I think if it didn't have these characteristics and we ran into it, we would not immediately consider it life, and we would be more thinking it might be some kind of a machine or a robot or just we've been fooled entirely. But again, some people want to be a little more open-minded as to what they call life. But what we're really interested in as human beings psychologically is we want somebody to talk to. We want somebody who can understand us, and we want to be able to understand them. We want them to have some kind of life force in them and not just be a stimulus response robot that parrots back whatever was programmed into it by whatever life forms made it long ago. That would be less satisfying, I think we'd all agree. So my first argument is that all of these actions are complicated. They require a large number of so-called degrees of freedom in the entity that is doing them. So this is a concept from information theory. How many degrees of freedom does this thing have? Even the simplest life form is actually extremely complex. They're made up of untold numbers of atoms, and the atoms into molecules, and the molecules into proteins and amino acids, and lots of stuff to do all the things that are required for something to be alive and to perform any kind of imitation of what we just talked about. So that immediately puts a big, strong complaint against anybody who wants to argue that, oh, well, life could be just about anything out there. No, I think most biologists and most scientists would, if you really push them to the wall, they would say, no, I really don't think there can be life based on anything except carbon. We know the chemistry of all the chemical elements out there. We know their ability to bond with other atoms and to make molecules. And there's only one that's capable of building complex structures, and that's carbon. Carbon has 4 bonding sites, and the bonds are just the right strength so that they're not too strong, like silicon's bonds, and they're not too weak. And they're capable of building things that have a little bit of toughness to them, given the right, environment. And they can bend around, and they can bend back on themselves. You can make buckyballs, you can make long chains, you can and then hang methyl groups off of that, and you can just build all kinds of things. I mean, carbon is like the ultimate Lego, and all the other atoms, they aren't. Okay, they can fit in certain places, of course, within life. In fact, they have to. You can't make life out of nothing but carbon. But without carbon chemistry, it doesn't seem like we could have the complexity necessary, simply from information theory. So of all the 92 elements, that requires one to be happy, and that's carbon. So evolving simplicity into complexity requires a special environment. If it's too cold, then what happens is the molecules, which need to be able to, after all, do things, the things we talked about for what life is, evolve and adapt and reproduce and fight for a niche and satisfy its energy needs and so forth. Those all require doing. Those are not static things that you can just sit there and have it all happen. So if it's too cold, you get frozen. And if you're frozen, then you're not going to be able to accomplish anything. You're basically dead. If it's too hot, then what happens is, of course, remember what heat is. Heat is really just a temperature is really a numerical means of talking about the average speed, the average kinetic energy of motion of the thing you're talking about. So if it's too hot, then what happens is the molecules are banging around so hard against each other, they basically pulverize themselves and they break apart. And if you get even hotter still, like in stars, then you even start knocking off electrons from the individual atoms. And then you're back to ultimate simplicity again. And ultimate simplicity is not life. Now, these are more cosmological. Here, let me do this. So, in order for an environment to be warm, we need it to be not on stars. Stars are too hot. Even the coolest stars are too hot. And we can't have it out in the middle of intergalactic or interplanetary or interstellar space. Well, maybe interplanetary, let me take that back, but not, it can't be out in interstellar space because the temperatures are too cold. Now, if these things are complex, they require a lot of stuff. And so we need, in an expanding universe like we live in, for the universe to, yes, expand on large scales so that it can be long-lived. If the universe instead were collapsing, then, you got a ticking time bomb. First of all, it had to expand at some point to get out to where it is, and then it has to come back, if that's what we're talking about. And coming back is going to heat it up and destroy all life. So you need an expanding universe, at least at some point, so that it can be long-lived. Black holes are extremely simple. There's only 3 quantities that describe a black hole: the net charge, the mass, and the angular momentum. Everything else has been crushed into the black hole, and there's nothing else that you can see from the outside that has any complexity to it. So you're not going to have life in a universe that is nothing but black holes. So then the next thing, assembling complexity requires time. Requires a lot of time. So evolution by natural selection, brief review of what that means. So if you have a life form and it gets a random mutation in its DNA that is reproducing, and the random mutation happens to make it better at doing what it needs to do to survive, then it's going to tend to leave, it's going to be more successful. It's going to tend to leave more offspring, and those offspring, to some extent, are going to inherit that new favorable characteristic. And so they'll be more successful, and they'll tend to leave more offspring. And so as you go on in time, then you basically begin to occupy a more and more higher and higher fraction of the population. And this is how favorable characteristics tend to propagate. If on the other hand you get a random mutation and you end up with, severe birth defects or severe defects of one sort or another, then you tend not to survive. You don't tend to live long enough to reproduce. And even if you do, then your progeny probably have a lower odds of doing so. And again, so unfavorable characteristics tend to die out in an ongoing population. But still, these random mutations are random, and so you never know when you're going to get one that actually helps you. You could argue, and we think it's true, that most of the changes that you do by random collisions between gametes in sexual reproduction, or even more especially, I suppose, cosmic rays coming in and zapping through your skin and knocking your DNA around a little bit, most of those mutations are going to be unfavorable and are not going to help you, and they're going to hurt you. So to assemble complexity that actually works requires time. On our planet, we know it took 5 billion years to evolve life forms capable of higher intelligence. Almost 5 billion. So the laws of physics must permit stable environments for a long time. If you don't have laws of physics that permit stable environments for a long time, you're probably not going to have a living universe. So in the standard model of particle physics, which has been very successful at accounting for everything that we see, the only thing we don't like about it is it's got 23 parameters, and that just seems like a lot, and seems to require a lot of fine-tuning to get everything to work out just right. But other than that, in terms of like how successful is it in accounting for the observations of everything we see, it's very, very successful. Okay? There's millions of ways you can take those 23 independent parameters, and I don't really mean millions, I mean billions and trillions and quintillions of ways that you could have these parameters that describe the 20 independent variables in the standard model and have them come out in a way that doesn't permit complexity to evolve. And that would be a sterile universe that doesn't have life. We clearly don't live in such a universe. So the first thing you might wonder is, well, gee, I guess that must be proof that there's a God out there. And he must have just been hard at work dialing the dials of the 23 parameters and getting everything just perfectly tuned right so that we could have this beautiful universe that we live in. No, that's actually not required, but it is tempting. I'm going to actually do this whole presentation, including the Astro 4 material, because it gives me a chance to talk about the multiverse. And if any of you are in my Astro 4 class, then this will be valuable stuff as well. So were we just very lucky? Again, there's only one atom in the entire periodic table of 92 elements that are stable against radioactivity, permitted by the laws of physics everywhere. There's only 92 chemical elements. Maybe I should also tell you that. There isn't any other stars or galaxies or anything where there's brand new elements that have no relationship to the elements that we all know in our chemistry class. No, the laws of physics are very well verified to be the same everywhere, all the way out to the edge of the observable universe, at all times, all the way back to the beginning of the universe, at least, within a small fraction of a second. Okay, so were we just very lucky? You're tempted to think so. But what if I told you that this is no coincidence? I do like the Matrix. So either we were incredibly lucky that the one and only universe that has ever existed or ever will exist happened to have a rare set of laws of physics which allow life, or number one, there's a God, But then where did he or she or it come from? If he can be eternal, why can't the universe be eternal? And if he can create all this incredible complexity, then he's got to be just as complex, if not more complex. So, sorry. So that doesn't really solve our problem, does it? Postulating a God leads to circular reasoning doesn't really solve the problem of the origin of complexity from simplicity. Physical laws, on the other hand, show how complexity evolves naturally from simplicity. There's no doubt other sets of laws that could have had this property as well. I don't want to argue that the only possible set of 4 physical laws and 20 free parameters that describe them that we have is the only one that can permit life. That would be way too big a statement. I'm not going to claim that. I don't think anybody can claim that. But all I would claim is that of all the dice that you can throw, remember Einstein said God doesn't throw dice? Well, he kind of actually does. But of all the dice that you can throw and all the ways that you could cook up a universe, I'm only going to argue that the ones that work out to have properties such that you can have life in them at some point is small. It's and probably very small. So we have a better solution, and that is the inflation paradigm. So it was realized about 30 years ago by Alan Guth at Stanford University that the known laws of physics permit a weird phenomenon called inflation. That if there is a field, we already know that there are various energy fields that do exist in the universe. The gravitational field, the electromagnetic field. Now we know we have the Higgs field as well. And if there is a field that describes the energy state of the universe, and if the universe can move between energy states that are semi-stable, then you well, I got ahead of myself a little bit. The inflationary paradigm starts with the realization that if you pack energy density into empty space, it has a negative gravity. So that's already implicit in the laws of physics. If you put energy into not something, but into nothing, empty vacuum space, it turns out it will have a negative gravitational effect. In other words, it will expand. It will cause space to simply expand. And so a universe that has that would be a universe that would be so-called inflating. Now, it's all a quantum process, and you can think of the energy state of this expanding, inflating universe as a whole bunch of little marbles wobbling around in this whole area. I mean, every little piece, every little part, every little tiny volume of the universe has its own little wobbling around in a quantum uncertainty sense. And it could tunnel right out of its semi-stable energy state into a state with much lower energy. And in that case, it would then expand much, much slower. And in this way, we think that we went from a state of being in this eternally inflating universe into a series of bubble universes. And our universe is just one bubble, like maybe that one there. And it's separated out from the expanding fluid. I mean, in some sense, this diagram is misleading, because if you get too literal about it, you think of a bubble blowing up in a very static liquid, but it's actually the other way around. It's the surrounding stuff it's this part here that is eternally inflating extremely fast. I mean, faster than I can possibly describe. Way fast. Okay? And these are bubbles that so-called nucleate out of that and then get left behind. And they nucleate out by tunneling through this energy state of this inflaton field, whatever it turns out to be. And we know only a little bit of its characteristics and really not much else at the moment. But we know it's possible, and we know that the inflation paradigm has predictions which can be verified, and it also solves problems that we don't have any other way to solve. So most astronomers and physicists are very much on board with the inflation paradigm as our ruling paradigm, and it's going to take something that can do all the jobs that we need doing even better before we're going to abandon the inflation paradigm. This is all consistent with quantum mechanics, which is a very well verified theory. So what we have is not really a universe on the biggest scale, but a multitude of universes, or the so-called multiverse. That's a term that I hear mostly, and it's a good term. I like that. Of course, there is this semantics problem, and that is the whole notion of the universe is that it is everything. And now we're saying that the universe that we live in and the universe that is accessible to us is not everything. So that's why I like using the term multiverse. And I think that's why a lot of physics people like doing that. Okay, what do I want to say here? So universes could be created out of this vacuum. And the total energy of those universes would be exactly zero. But out of zero, you get something. A universe from nothing.